Howdy everybody, welcome back to the Zelda 2 tutorial. Last time we set up the player with the step event, and we are now ready to get started on building in the state system so that the player can move around. So let's get cracking on that. So I've already increased the size of the text here, and yell at me whenever I forget because I always forget. Anyway, so we have our player, we have ground checking, all that fun stuff. Eventually, after we've done everything that would be involved with after we do everything that is involved with, so after we have done everything that is supposed to be executed pre-state, so stuff like damage checking, because damage checking will change our state to the damaged state, and transition checking to see if we've reached the end of the room and we're supposed to be transitioning to a new room, or if we're trying to talk with other people, so that puts us into a talking state, etc. These are all sorts of things that are kind of persistent across different states. Once we do all that, we actually execute the state that is currently being triggered. So we need to go about doing that. We start off with the move state because that's what we set up our player with right over here. State and previous state is move. And let's pull up some code here. All right, so we have our move state that we're going to be setting up here. To get it started with, I'm going to collapse all the regions on the other side over here, and we're going to set it up over here. Pound region states, region, and a little copy paste, 2, 3, 4, and 5. You're going to be states, acceleration, speed fractions, collisions, and movement. And last but not least, animation. These are our basic sort of state actions. So first off, we check our state to see if this is the state that we should be in, or if we want to move to a different state. Then we check to see what kind of acceleration our player wants to add to our character. Then we check to see our speed fractions. So we want to keep our player in integer solid locations throughout all this process. We could do it with floating point error by just not bothering with speed fractions, but then that allows for floating point errors where you can end up with two things being in the same position at the same time, and is part of in the lot of older video games where you see glitches known as zips and zooms, where they use a subfraction error, positional error, to get the player and a object or the wall in the same place at the same time, and then that causes the game to force the player up or to the right or something, depending on what the game logic, and that will cause them to pop out somewhere else in the game, depending on where they want. So by using speed fractions, we eliminate the possibility of that happening because we're always in an integer location. Collisions and movement be, of course, our movement and animation. Once we know how fast we're moving and if we are moving at all, we might end up just having 0 as our how many pixels we're going to be moving. So that would be a possibility. Then we can animate our character appropriately. So starting off with our states. Well, we have a bunch of, so one of the key things about the state system is each state knows what states it can enter into. So in this case, the move state can enter into 3 other states. We'll just put these in here for now. We aren't actually doing anything. So jump state, duck state and our standing slash state. So the player, when he is in the movement state, he can jump, he can duck, or he can do a slash, a standing slash. And that's a key feature of the state system, knowing what actions you can possibly do at any given time. And this carries on to basically any game you play right now. You know, there's a lot of games like, let's say, Super Smash Bros. For a common example. When you are in a certain state, like say you're in the shield state, you can't attack or something like that because you're shielding yourself at that point. And when you're doing a smash or something like that, you can't immediately jump into another attack because you're locked into your smash attack or something like that. I believe. Don't quote me on this because I haven't played Smash since GameCube. So yeah. But anyways, you tend to be locked into various different interactions that you can possibly do per game. So acceleration is going to be our first full setup we got going here. For the player, when they are walking along on the ground, so let's come over here to the room a little bit so we can see the player. He's going to be walking left and right, and we don't want him to immediately jump to the maximum speed because that would be bad. I mean, there's some games where it's good to do it that way, but in the case of Zelda 2, we use a more lurpy sort of additive acceleration where the player slowly speeds up, and then under the same principle, you can then press the left button while you're going right. So you do a skidding, and then you start going left, and once you skid to a halt, and you'll see this a lot in actually Mario, Super Mario Brothers. That's the where you see it a lot. It's exactly the same thing. And so we're going to put in a additive acceleration system here using all that code I talked about earlier. So remember our current acceleration and our I got it all. So our current x speed and our applied x speed, and I was kind of light on the details of why we have these things instead of just our x speed, y speed like previously. Well, previously I've been using stuff like this. A second here to copy it out. Previously, I've been using stuff like this. X speed is equal to clamp x speed to minus walk speed. Walk speed. That's the wrong one. Here it is. That's just dead clamping the speed. Here we go. So I would be approaching the walk speed towards the sign of the input by ground acceleration or approaching to zero by the ground friction. And that worked pretty good, except it's more of a linear acceleration. You would have 0, 0, 0, 0, 0, 0, and then 1, 1, 1, 1, 1. Eventually, I have it all written out here in my math setup here. So this would give you results like this. You would have 0, 0, 0, 0, and then all of a sudden you'd be at 1, 1, 1, 1, and then it switches between 1 and 2 pixels every frame after that because that's just the way the math works out. But when we do a lurpy acceleration, as we are currently doing, we get a more 0, 0, 0, 1, 0, 1, 0, 1, 1, 1, 2, 1, 1, 2, 2, 1, 2, 1, 1, 1, etc., etc. So instead of being directly from 0 to 1, you get some intermittent steps. And this is actually really good because it makes it a lot easier for the player to tap right or left to move their character by 1 pixel to really get that accurate positioning, which is something that a lot of games, especially when they're just doing the linear acceleration, you can't really do that because you had a whole bunch of zeros in a row. So if you try to tap to move over by 1 pixel, well, you're just going to have a bunch of zeros. You're just going to have zero added to your x position each time. So you, but if you're using the Lurpy acceleration, we have a couple zeros, but then we have a 1. So after that, and that makes it much easier to tap left or right to move by 1 pixel when you're set up this way rather than the other ways. So there's a lot of benefits to the setup here that we got going on. So this requires us to have a current x speed, which would be what our x. We're basically moving our x speed towards a position, and then we set our applied x speed to that current x speed. Oh, yeah, I should probably actually finish up this before we move on. Additive acceleration. Last but not least, wall checking. If wall on the left and sine of x output is equal to -1, or wall on the right and sine of x output is equal to 1, then current x speed is equal to 0 and applied x speed is equal to 0. So basically, I'm saying if the person is trying to walk into the wall on the left or the right, just make my speed 0. And that means when your speed is 0 and we go to animation, if your speed is 0, then your animation is none. You have no animation. You're in the idle state at that point. All right, so I believe I have all that information there. And speed fractions are pretty simple as far as it goes. They're the same as they've always been in my previous tutorials, except the math looks a little bit nicer now because I'm using these fraction and int64 functions to more easily convert from decimals to integers. So basically, what we're doing here is so what we have here is we floor fractions, which removes acceleration, boosting when starting from the stop. So if you had like a y fraction of 0.6 and you didn't zero it out when you come to a stop, then you would end up with sort of a 0.6 of an acceleration, pixel of an acceleration, just sort of hanging out in your left right clicking. And I mean, you could want that even, like I was saying, some games that let you by when I'm talking about the linear acceleration, you would save the x fractional inputs and basically use that as your way to tap out of tap over by 1 pixel or the other. But I think it looks kind of ugly, so we got that in there. Then we add back our fractions to our x and y speed. We have our x fraction and y fraction. So whatever it was previously, starting off, it's just 0 because, well, that's what it is. Then we take our x fraction and we set that equal to the fraction of the applied x speed. So frac gives you the decimal present. So you get 10.2, frac returns 0.2. Then applied x speed is equal to int64. What this basically does is drops your decimal place. So now you have your 2.2 becomes 0.2 on here, and this becomes 2. And that means that next frame will add that 0.2 back to here. So if you're at 2.8 at that point, then you'd end up with 3, and x fraction would be 0, y fraction would be 3, etc. etc. So that keeps us in our pixel perfect positions at all times, presuming you place the player in a pixel perfect position to start. All right, collision and movement. Uh, so I added some heuristic stuff. X speed previous, Y speed previous is equal to applied XY and speed here. Just some information that you might find that you might be able to use to determine special animation states and stuff. Our var underscore speed is equal to move with collisions. So we tell parent solid as the parent object in our collision, and applied x speed is our x speed, and applied y speed is our y speed. Move with collisions is a special script here that is included with the base project. Move with collisions. Start from here. It is fairly complex, and in all reality, I way over provisioned it. I need to go through it and make it much simpler because it takes too much processing time to as it is right now. I mean, it's fine for the player object, but if you have tons of different things on the screen at the same time, all trying to use it, it starts to slow things down, and I need to make it simpler. So make it simpler. That's the way it always works, you know. The basics of this is let's go over this real quick. With solid object testing, if y speed is greater than 0, we are going down. X movement perverted over y for easier ledge landing. Then, if place meeting x plus y speed solid. While place meeting x plus x speed y solid, and x speed does not equal 0. X speed equals approach the x speed towards 0 by 1. So this is basically a lot like Sean Spalding's collision code, except I was trying to make it somewhat different by using while loops and stuff instead, and it basically gets you the same thing. But I was thinking, oh well, maybe we could just adjust the x speed directly instead of moving by 1 pixel each frame, or well, each iteration of the loop. So instead of moving 1 pixel each iteration of the loop, I adjust the x speed by 1 pixel each frame until your x speed is no longer causing you to touch the solid object. At which point, then it applies whatever x speed you have. And so it's just it gets you the same thing in the end. It's just a different approach to get to that place. So and then of course when you're going up or staying flat, y movement preferred over x. So I'm actually particularly proud of this little improvement because it is actually a very big improvement over the normal collision code, because you have the you have a differentiation between your going up and going down, which makes it easier for people to land on ledges or to not get stuck on ceilings with jumping near cliffs, and gives extra frame of coyote time going over ledges. And same thing over here on our tile collisions. So this is our object collision testing. Tile collisions are very similar, except in this case, I have it set up so that when you are landing on a ledge, landing on a platform, or basically on a ladder, which is again basically a platform kind of thing. Zelda 2 doesn't really use this, so you can kind of ignore it, but you know, set it for your own edutainment, I guess. And then if tile meeting, so tile meeting is another script. This one is based off of the work by Pixelated Pope, and it uses tile collisions with a tile collision object to maneuver an object around that is then used as the basis of an object collision test that emulates the function of tile collisions. The main reason why we're doing this is because it will hopefully make it easier to do slopes later on in the future. I'll get around to it eventually. I'm just still working on the process. So, anyways, you can kind of ignore it or copy what I showed you there if you want to for your own stuff. But or you're free to input your favorite collision system right here too. Like I said, Sean Spalding's. You can just throw that in right there as well. Then basically what we're doing afterwards is send our applied X speed and applied Y speed to whatever pops out of the collision system. That if we are going to hit a wall or something, it will slow us down to the appropriate speed so we don't go into the wall. And then we add to our X and our Y the applied X and the applied Y speed. Part of this is all the collisions are self-contained inside of the code. So the application of the X and Y at whatever point doesn't really matter, unlike in Sean's Fallen code, where you have to apply the X before you calculate the Y, or else you'll end up with some wall collision functionality problems. So last but not least, animation. This should be fairly easy. If the current X speed is equal to 0, then image speed is equal to 0, manual sprite change is equal to true, and sprite index is equal to idle. Basically, this is idle state, except I didn't bother making the idle state its own state because the idle state doesn't really do anything interesting. It's just Link standing there, and this is easier than having a whole state just dedicated to being idle. So, else, image speed is equal to animation speed, which is, for our purposes, 1. And that will actually become more important later on because I'm going to be implementing a slow motion system in the future, which will let you adjust the game speed on the fly, except you aren't adjusting the game speed because that's bad. Then we have image X scale is equal to the facing direction. If it's equal to the right, then our image X scale should be the absolute value of image X scale, which is basically saying, okay, if your X scale is negative 0.5, it's now 0.5. Or so in this case, facing right. And the reason why we're doing this ABS thing is so that if you do have if you do have a negative, if you do have a value other than 1, or if you have a value other than 1, then you would this would allow you to have different image X scales. So you could have a 0.5 or 0.75 or whatever if you want. And of course, increment our frames in state animation counter, which is very important for animations coming up in the future when we do animation states. All right, I think that's everything for this. You won't see them, but I cut out a couple of problems at the very beginning. But so actually, let's see if we can actually test this at this point. As Link should be able to move, we go into the game. Or else it's going to crash. That was the last time we have happening. Do some debugging. And let's see, object link side scrolling, document solid, not set for repeat. Alright, you go over to objects. Let's see, game objects. Create an object. Parent underscore solid. And this should actually be its own group. Parents and move you down to parents. Solid, give you a sprite. Sprite solid. Alright, let's try that. Object tile checker, not set for. I should probably set the tile checker object as well. So in your objects, this would be a game object at this point. Object and object tile checker. What we want to do here is give you a sprite, and for you, what was it? Go to sprites, miscellaneous, sprite collision checker set. To that guy. Sprites. that is miscellaneous. Right tile collision checker set. So it's basically just a set of tiles that emulate the collision tiles that we currently are using. Because this is going to be used for object collision testing. Alright, third time's charm, right? And Link is missing. But he can move wherever he's at. I presume he's fallen through the floor or something. I don't have to restart that yet. So. Anyways, well, Link is moving despite the fact that we can't see him. We'll probably figure out what he's at eventually. Thank you everybody for joining us, and take it away past me for some Patreon sponsors.
I'd like to thank my Legacy Patreon sponsors, James Burton, JD Lowe, Suli, and Vazia. I'd also like to thank my current Patreon sponsors, Kenneth Klein and Vladimir. Your support helps the NESGameMaker be made and to continue to grow, and I hope that you all continue to have good luck with your programming.